Hey, welcome back AP Calculus students. Today we're looking at 3.3 rules for differentiation. Well, this is part one, so we're going to spend two different classes on it because it's a lot of new stuff. It's not necessarily hard stuff, but I wanted to kind of give us some time to process this first part before we jump into the second part. So on the top, we're doing just different versions of different rules for differentiation. So the first thing we did, we're already familiar with this. This is the power rule. Right, so anytime we have x to some power or some exponent, what we can do is we can drop down our exponent and then subtract 1 from the exponent to get our derivative. It's pretty straightforward. The second one is also pretty easy. The derivative for any constant, so if c is a constant and we're finding the derivative of it, it's going to be equal to 0. And then the last one says that if we have an addition or subtraction and we're finding the derivative, we can do it by finding the derivative of each part. So we have a u here, and we're adding or subtracting the v. So we can find the derivative of u with respect to x, and then we can add or subtract the derivative of v with respect to x. So nothing too groundbreaking here, but it is the foundation of it. So let's look at the example. It's asking us to find the derivative of p with respect to t. So something different, right? We're used to seeing the derivative of y with respect to x, but all it's saying is that p is our function, right? That's the same thing as y. And then our t is our independent variable, which is what our x would be. So just don't let the letters fool you. All it's saying is the top is the function, the bottom is the variable. Okay, so they're giving us our p. Now we're going to apply all of these rules, right? All of the top three rules to this to get to our derivative. So let's say p prime is equal to, and let's do the first part first, right? Because the third rule says that we can take this in parts. So we're going to apply the power rule to t cubed. So we drop our 3 in front, our t, and then we take 1 from the 3, so that's squared. Okay, second part. For now, when we do this, one of the rules from earlier says that we can take the constant out when we're finding the limit, or not the constant, I should say coefficient, the 6 out when we're finding the limit. So same idea as when we're doing our differentiation. We'll keep that 6 there. We'll drop the 2 down. We'll subtract 1 from 2, which is 1. So we don't really need to put first power there, right? Because, we never put first power. We just put the variable. So this whole thing is just going to be 6 times 2 is 12t for the second part. Now again, well, either way, you can just keep the 6 there and just say we drop down the 2 and we got to multiply it with whatever's in front. Okay, so 6 times 2 is 12. And then we have t to the first power, but we didn't write the first power because we don't write first power on anything. That's just not how it works. Okay, the third part. So we're going to have minus. So t to the 1 power, right? So let's do this over here. Let's do negative. Let's just do 5/3 t. Now anytime we're finding the derivative of just t, this is what happens. If we don't have a power there, we can put 1. So we're finding the derivative with respect to t of 5/3 t, or 5/3 t to the first. All right, so what happens is we drop down the 1, and then 1 minus 1 is 0. Okay, so well, the 1's not going to affect it, right? So it's just still 5/3. And then t to the 0, anything to the 0 power is 1. So this whole thing is 5/3. So anytime we're deriving just the variable x or t, it just goes away. And we're left with whatever coefficient we had in front. So this is going to be 5/3. Okay, and then the last part is this thing. Right here, right? This is a constant 16. There's no variable attached to it. So the derivative of that is 0. We don't even have to add that on because adding 0 doesn't change our value. So p prime is going to be 3t squared plus 12t minus 5/3. And we're just applying the power rule to each part to find the derivative. Okay, next one. Finding horizontal tangents. It's asking us, does y equals x to the fourth minus 2x squared plus 2 have any horizontal tangents? If so, where? Okay, so horizontal tangents. Now, horizontal tangents, remember the slope of a horizontal line is 0. So anytime our slope equals 0, then we have a horizontal tangent. Okay, so we could graph this. So one way we could do this is we could graph it. Okay, so let's do that now. So we're going to do y equals, and it's going to be, what was the thing for it? X to the fourth minus 2x squared and then plus 2. We can graph it, and then we can find the places where the slope is equal to 0. And this is a good time to talk about mins and maxes. So notice that we have a minimum there. Our slope would be equal to 0 there. A local max there. Our slope would be equal to 0 there. And then another here. So we find that we have horizontal tangents anytime we have a local minimum or maximum. So what we can do on our calculator is we can calculate these. So let's do calculate. So we're going to hit second. Calculate is the trace button. And we want to find where we have a minimum. Right? So when we do that, what we're going to have to do is we're going to set up boundaries, because our functions could have more than one minimum or maximum in an area. What it's asking us to do is set up boundaries so it knows where we're looking. So we need to make sure that we set up our cursor anywhere to the left side of that minimum, because it's asking us to find our left boundary. So we're going to hit enter there. We're going to scroll anywhere to the right of that minimum, as long as it's not catching two minimums in our boundaries. And then once we do that, it's going to ask us to guess. So we're going to have to do this, hit enter 3 times in total. And then it says we have a minimum at negative 0.999999 and y equals 1. So we're going to assume that that 0.9999 is the same thing as negative 1, and our y is 1. So we're going to go back here. So from our graph, we said we had a minimum at negative 1. Well, let's just write it as a point. It's probably neater that way. Negative 1, 1. Okay, let's go back and find some more. Okay, so we're going to calculate again. This time let's find the maximum, the one that's in the middle. Whoops. That's not what I wanted to do. We're going to find the maximum. We're going to set up our left boundary anywhere to the left of that maximum point there. We're going to set up our right boundary any place to the right of that maximum point there. And now that we know that the maximum is between those two little dotted lines that go up and down, we're going to hit enter. And it says that we have one at negative 8.2372 e to the negative 7. So that's very close to 0, right? Because negative, this is in this format that they're giving us is in scientific notation. That means that there's actually 7 decimal places to the left of where the actual decimal is. So we're going to assume that's equal to 0. And then it says our y equals 2. So we'll say, all right, we have another one at, whoops, that's not the one. 0, 2. This is our max, min, and then we have one last one that we're going to find. That's a minimum over here, so we're going to calculate the minimum value. I'm going to set up our boundaries again, one to the left and one to the right of that minimum point. It's going to guess, and this time it gave us the exact answer, 1, 1. So that's awesome. And then 1, 1, which is local min. Okay, so that's what would happen if we did this using a graph, which is fine, and that works. And a lot of the calculus stuff, you can find the answers in different ways. It's just that one way is probably faster than others. So just because you forget something, don't think that you can't do it in any other way. Like, there's other ways to do it. So the second way we could do this, because we're talking about the slope, well, anytime we're talking about the slope, we should be thinking about derivative, right? So derivative. All right, so let's take the derivative of y. So y prime is going to be, well, the derivative of x to the fourth is 4x cubed. And then the derivative of 2x squared is 4x. And then the derivative of 2 is 0, right? So this whole derivative, the derivative of the whole function, x to the fourth minus 2x squared plus 2, is just 4x cubed minus 4. Now also we know that the slope is 0, so that means we're looking for when the derivative, when is derivative with respect to x of y equal to 0. So anytime we see horizontal tangents, we're looking for when the derivative is equal to 0. So all we have to do, since we found the derivative, is we're going to set the function equal to 0, and we're going to find all the x's that make this true. And we can do this using algebra because we can factor this thing out. So notice that each of these terms, they share a 4. We can factor the 4 out. They also share one of the x's. So we're going to say 0 equals 4x. We're factoring that out. Inside, we're left with, from the first term, x squared. And then we factored everything out from the second part, so we're left with 1. Now, let's factor this thing. That's a difference of squares, right? So those of us who are super good at algebra, we know that it factors to x plus 1, x minus 1. Now, referring back to algebra and the zero product property, that if we have 3 multiplications or any amount of multiplications, just multiplications, and they're equal to 0, that means that one of those things, if not all of those things, or some of those things, has to equal to 0. But we definitely know that one of those things has to be equal to 0, because the only way to multiply things and end up with an answer of 0 is if one of those things is 0. All right, so what makes the first part 0? Well, that's 0. What makes the second part 0? That's -1. What makes the third part 0? That's +1. So notice that this is the same thing as all the x's that we found using the graph. So just another way we can use calculus and the idea of derivatives to find something, to find horizontal tangents. All right, the next one says the graph has 3 horizontal tangents. At what points do they occur? So we could treat this the same way, right? We could go ahead and do the derivative, but notice here, the derivative of that thing might not be so good when we start factoring it. So let's use our calculator, and let's just do the same thing where we found the mins and maxes. So we're going to plug in our function to our calculator. We have 0.2 x to the fourth minus 0.7 x cubed minus 2x squared plus 5x plus 4. Okay, so let's look at what the graph of this looks like. Okay, again, we're just finding the mins and maxes here. We're going to go to second calculate. The first one is a minimum. All right, so we're looking at this point here. We're going to hit enter. And then enter to at some place to the right of that minimum point. Hit equals. So the minimum here is negative 1.86. I think usually the standard is 3 decimal places when we're rounding in calculus. So let's just go ahead and say for this one that it's 1.862. 862. And then 5.321. Negative 5.321. Okay, let's do the same thing for the maximum here. Left boundary, right boundary, guess, and that's 0.948, 6.508. Okay, go back here, put it in. And then we'll do the last one. Calculate that one's a minimum. Left boundary. Right boundary, enter, 3.539, 3.539, and negative 3.008, negative 3.008. All right. So the reason why we did this one calculator and not using just the derivative is because even though we can derive that, when we set it equals 0, there's so many terms in there and we got the decimals that we were probably not going to come out with whole number solutions. So yeah, I mean, the calculator made our job easy. There's no way we'd factor to get those numbers. It'd probably be impossible. And we couldn't use quadratic formula because it's not a quadratic function. Right, so that's pretty much it for today. Hopefully that wasn't too much. So again, we just covered the idea of differentiation, right? So we did the 3 rules. We did a derivative of our function p here. Then we talked about horizontal tangents, and the important thing about horizontal tangents is that, well, one, we can use our graphing technology, right? We can graph our function. We can find the mins and maxes because the mins and maxes give us our horizontal tangents, right? We know that there's a slope 0 at horizontal tangents. Okay, we also found that if we can derive it and set it equal to 0, we can use that to find our derivatives as well, or our horizontal tangents, excuse me, as well. And then the last one was just another example. It was more of a calculator practice because we couldn't use the derivative and set it equal to 0 to find our horizontal tangents. All right, that's it. We're going to spend more time on this section next time. But for today, very good job.